Okay, so we're very happy to have here to give the last lecture series of the HMS focus term, and to speak on Picard-Fuchs uniformization and Calabi-Yau geometry.
Okay, well, thanks to the organizers, and it's been an unexpected pleasure to participate in the homological intersymmetry semester this year. I thought nothing was going to be going on at CMSA, and I'd be spending all my time in Providence, so it's been very nice. So the title today, and it's the title for today, there's a new title for Thursday, is Picard-Fuchs uniformization and Calabi-Yau geometry. And I've tried to organize, if you look at the abstract, part 1 and part 2, I've tried to organize the lectures in such a way that there's a complete thought after each part. So for those of you who feel the need to escape at the break in the middle, you're welcome to, of course, and you'll be missing good stuff, but at least it's a well-defined chunk that you've seen before and would be missing out on. So because I have 4 hours and because Natty specifically asked me to not assume a lot of stuff, in fact there was a list of words I couldn't assume, I'm going to make it very what's the word, accessible, okay? So bear with me in that sense if it seems too easy, and feel free to ask lots of questions. So as the title suggests, the basic objects of interest geometrically here for us today and Thursday are Calabi-Yau manifolds. Okay, manifolds, varieties, use your appropriate adjectives, whether you want them to be singular or not, so it's up to you. But what we generally agree on is that we want the canonical bundle to be trivial. We may or may not want to assume that the fundamental group is trivial. I certainly don't in complex dimension 1. So examples. Well, the examples that we all love to give first are the hypersurfaces of degree n plus 1 in Pn. Okay? So, of course, if we take n equal 1, this is why we don't impose that caveat about simply connectedness. I'm sorry, n equal 2, I want here. I'll do n equal 1 in a second. So this will be Calabi-Yau 1 folds, okay, and they're just cubic plane curves. Okay, and this is the AKA column, also known as elliptic curves. Okay. So n equal 2, we just did. N equal 3, so Calabi-Yau 2 folds. Well, now without this restriction on the fundamental group or on H1, we would allow ourselves to consider abelian surfaces in this class. But let's impose that additional restriction. And since we're talking about specifically examples in this setting of hypersurfaces of degree n plus 1 in Pn, we're stuck with what we get. And what we get are quartic surfaces. Okay. Now, there is a classical connection between abelian surfaces and quartic surfaces due to Kummer. The observation there was that if you actually take a polarization on an abelian surface and you try your darndest to embed it in CP3, you can do so at a cost, and the cost is 16 ordinary double point singularities. And this is the famous Kummer quartic realization. But the more modern way to look at that is once you've embedded it as a quartic surface with 16 ordinary double point singularities, you blow them up, and you get a smooth surface, which is not an abelian surface. It's a K3 surface. Okay, so this is also known as K3 surfaces. Okay, we go to n equal 4, and we're dealing with Calabi-Yau 3 folds. Okay, and the famous example here, of course, is the quintic 3-fold. And then we get to have this also known as column, and we say, oh, wait a minute, also known as Calabi-Yau 3 folds. Okay, because these were new. Okay, so this is an extraordinarily interesting class of manifolds or varieties to study. But it's also interesting to ratchet this back a little bit and look at the primitive case of n equal 1. So in n equal 1, we're talking about Calabi-Yau zerofolds. What's a Calabi-Yau zerofold? Well, remember, my examples are hypersurfaces of degree n plus 1 and Pn. So Calabi-Yau zerofold is a hypersurface of degree 1. Degree 1 plus 1 is 2 in CP1. In other words, it's a pair of points or a double point. Okay? So a pair of points. Okay, and this is not just a game. I mean, this is really important in what comes later to consider these. Now, of course, sometimes in this source of examples of hypersurfaces of degree n plus 1 and Pn, you get lucky and you get everything. Okay? So in particular, for the cubic plane curves, well, elliptic curves, all elliptic curves can be realized in various normal forms as cubic plane curves. Think the Weierstrass normal form if you like. Think the Legendre family, whatever you prefer. But it's an important fact that although a chordic surface is a smooth chordic surface is a K3 surface, okay, this only goes one way, okay, not the other way. So not all K3 surfaces are quartics. All right. Well, once you accept the fact that not all K3 surfaces are quartics, you have to sort of ask yourself, how do you get your hands on K3 surfaces? Because the beauty of having this classical relationship between elliptic curves and cubic plane curves, the power of that normal form is that you're able to have a dictionary between transcendental and algebraic quantities that's very, very rich, very, very rich and very powerful. Ideally, you'd like to have that for all Calabi-Yaus. But to begin with, you'd better have a notion of a normal form for K3s that allows you to access the same kind of thing.
So my question,
yes?
how many of K3s are quartics, like in terms of, like, what's the maximum size?
Oh, okay. So, well, let me answer that with just the notion of a polarization. Okay? So we have the notion of a polarization, okay, that applies to K3 surfaces. In our example of quartics, okay, this is the hyperplane class. Okay, so you take a hyperplane in CP3, you intersect it with your smooth quartic, you get a quartic curve, and that quartic curve has self-intersection 4 by construction, okay? And that is the representative of the class in middle dimensional cohomology, which is providing the polarization, okay? So it's a hint as to how to proceed. So for K3 surfaces, K3s with polarization, okay, the answer to Nadi's question is countably many components of dimension equal to 19. Okay? And you get 1 for each n, and there are 2n polarized K3s. Okay? So intuitively, you can think of these countably many 19-dimensional moduli spaces of 2n polarized K3s sitting inside a single 20-dimensional moduli space of Kähler K3s. And there's a rigorous way to do this. I have to fiddle with the notions of coarseness. There's issues of realization of the families associated to them, but it is, in a period theoretic sense, natural to think of there being a 20-dimensional domain for the arbitrary Kähler K3s and a 19-dimensional subdomains for each of these. Okay? All right. So that's good. That's a hint as to how the story might look a little bit. Let's do a bit of a parallelism here between elliptic curve case, though, and K3 surface. Okay. So for elliptic curves, we of course have this intuitive picture of the topology, and I can put my alpha and beta cycle or A and B cycle, okay, marking H1 with integer coefficients. These span a lattice, kind of the only natural lattice that we should be considering here, which is this lattice we know is H. It's a signature 1, 1. Okay, just by construction. Okay, the self-intersection of 0 you see by moving the circles off each other, and the intersection of 1 you see by, well, they intersect at one point. Now you can soup this up by looking at the Hodge diamond for an elliptic curve. And the Hodge diamond, well, there's 3 levels of it, H0, H1, and H2, okay? And we have H2 splitting into H10 and H01, okay? Typically, we focus our attention on the middle dimensional cohomology when it comes to the kind of computations we'll be doing involving periods. So the part to focus on here is this middle bit. Okay. And then in terms of what kind of moduli space you get for elliptic curves, well, you have everything's over C. You have a one-dimensional complex structure moduli space, okay? And of course, it's a well understood story. Classically what this is, it's what's known as the J line, okay? And we'll talk more about the normal forms in a bit, but in effect what we're talking about here is that if an elliptic curve is specified as a special kind of quartic, let's say by y squared z equals 4x cubed minus g2x z squared minus g3, the so-called Weierstrass normal form, then J is an invariant you can attach to the elliptic curve, and J of E is g2 cubed over g2 cubed minus 27 g3 squared, okay, otherwise known as the discriminant. The denominator is the discriminant. So the theorem is that two elliptic curves in Weierstrass normal form are isomorphic if and only if their J invariants are the same. Okay, so this is a perfect invariant for the story over C. Now the question is, how much of this has a natural generalization for K3 surfaces? So first of all, you have to understand that focusing on the middle dimensional cohomology for a K3 means you're looking at H2 of the K3. And integrally, this gives you 3 copies of this same H lattice, and then plus 2 copies of the negative definite E8 lattice. Okay, so think the root lattice for E8, but make sure it's negative definite, not positive definite. And we often call that lambda K3. Okay, it's universal for all K3 surfaces. It's the K3 lattice. Okay, its signature is still indefinite, but now its signature is 3, 19. Okay, and the Hodge diamond is 1, and then it has some zeros. 1, 21, 0, 0, 1. So the middle dimensional piece is this 121 weight 2 Hodge structure. Okay. Now, what's important about the interplay between the algebraic and the transcendental when it comes to K3 surfaces is, first of all, that the 2, 0 and the 0, 2 piece can effectively be split off when you're interested in algebraic sourcing of middle dimensional cohomology. Okay? Because anything algebraic in the sense of algebraic curves on your K3 will contribute classes that live in the 1, 1 piece. Okay. So you can ignore, for these purposes, the 2, 0, 1 and 0, 2 and focus on the 1, 1 piece. And the so-called Néron-Severi of your K3 is contained in the H11 part. Okay. And this comes from the classes of algebraic curves. Okay. Now, as a sublattice of this K3 lattice, the Néron-Severi lattice itself has a certain rank and signature. So it's typical to say the signature of Néron-Severi is 1 comma rho minus 1, because you want its total rank to be rho, also known as the Picard number. Okay, so the rank of Néron-Severi equals rho, so-called Picard number. Okay, but what effect does this have on moduli spaces? Okay, well, intuitively, if our K3 surfaces are rigidified by being extremely algebraic, okay, you can expect that the number of moduli should go down. Okay, and in fact, there's a rigorous way of saying that, which is that the moduli space of what are called L-polarized K3s, where L here, suppose, is, I'll put quotes around it, Néron-Severi. So it's a candidate Néron-Severi group, 1 comma rho minus 1 signature. Okay. Now this moduli space has dimension 20 minus rho. Okay. So if rho is maximal, because the maximal rank when you're living in here is 20, then the moduli space is 0-dimensional. Okay? These are the analogs of complex multiplication elliptic curves. Very, very special K3s. Matthias Schutt and Noah Melkes did a whole bunch of analysis of when, how many of these exist and what are models for them when they're defined over Q. It's the whole story of CM elliptic curves writ large on K3s. When rho is 19, you get a moduli space that is the closest kin to the J-line. So it'll be 1 complex structure modulus. In the simplest cases, it will also have 3 special points. So the J-line has 3 special points, orbifold order 2, orbifold order 3, and infinite order. The infinite order is the cusp that we talk about in the J-line all the time. And the 2 and 3 also correspond to these special elliptic curves with extra automorphisms. So the analog of that, precise analog of that, you can do for a number of rho equal 19 K3s. So I'll just say here, rho equal 19 is the analog of the J-line. And it actually splits into 2 subcases. One is the case with cusps. So with cusps, so it's like a modular curve. And then there's without cusps, so it's like a Shimura curve. Okay, so 2 different kinds. Now, of course, I'm talking about changing the lattice when I talk about going from a K3 moduli space that looks like a modular curve to a K3 moduli space that looks like a Shimura curve. These are different rank 19 lattices that we're talking about. And we'll talk about some very specific rank 19 lattices in a little bit. Okay, any questions? All right, so let's make this really concrete in a class of examples that are very important and closely related to yes.
Modular space ML.
Yes.
So is the modular space of all K3s that have this specific Néron-Severi composition, or?
Yeah. So I have to. I mean, to spell it out very carefully, we would say it's the moduli space of K3 surfaces with a primitive embedding of the lattice L into their Néron-Severi. Right. We would mumble some words about markings because we have to be careful about that. And then we would also throw in the existence of a pseudo-ample class, which is a technical condition that is always going to be satisfied for the ranks we care about. Okay, so there are conditions you could say, okay, and subject to those conditions, you get a theorem of Nikulin and Dolgachev that says that this is a coarse moduli space for K3s of this type. Okay. And that's the best you can expect. You can't expect to get a fine moduli space here. All right. Now, there's more similarities between the elliptic curve case and the K3 surface case, even than is evident there. So so both elliptic curves and L-polarized K3 surfaces have moduli spaces that are quotients of a bounded symmetric domain by an arithmetic group. Okay, so let's take the elliptic curve case. Well, there, the bounded symmetric domain is the upper half plane, right? And what's the group? I never remember what side to write my slash on. Anyway, the group is PSL to Z. Okay? In the case of K3 surfaces with lattice polarization L of rank rho, well, we have a bounded symmetric domain of type 4 of dimension 20 minus rho, and we're quotienting by what's called O plus of the transcendental lattice, TL. Okay, so TL here is the orthogonal complement to L, so it's L perp in lambda K3. Okay, so let's do a reality check. Okay, make sure that we're not completely off base here. We're certain that this dimension is 1, arithmetic quotient of a 1 complex dimensional domain. What about this other one? Well, okay, so how is this going to work? The domain D4 20 minus rho, when rho is 19, let's say, okay? So for rho equal 19, we're looking at D4 20 minus 19, which is D4 1, which happens to be known as the upper half plane. Great, that's good, okay? We're happy with that. But now here's where you should get mad at me, okay? You're gonna get mad at me because this is an arithmetic subgroup of a matrix group of size 22 minus rho by 22 minus rho. Okay? And 22 minus rho is 3. Okay, so O plus TL consists of 3 by 3 matrices. And I have to say that this is a place where a lot of people get confused very early on in the game, and some of them throw up their hands and just move on. But it's not bad. It's not bad at all. What you have is a beautiful representation theoretic fact that also corresponds to a beautiful geometric fact. Now, the geometric fact is that the image of the period mapping for polarized K3 surfaces always lies on a quadric. So the number of periods for a rank 19 lattice polarized K3 is going to be 3. Okay? And projectivized, that means you lie on a CP2. Yes? Okay. But you satisfy a quadric condition, which means you lie on a conic in CP2. The conic is really just an embedded P1. It happens to be embedded with degree 2, but it's still an embedded P1. And the upper half plane we're talking about is an upper half plane on that embedded P1. That's all it is. Okay? So how do you translate that fact? So this fact is that periods of polarized K3s lie on quadrics. Okay? That fact is equivalent in this algebraic setting to the fact that O plus TL is symmetric square, okay, of a group of 2 by 2 matrices. Okay. Now, there's a cost, and the cost is that these 2 by 2 matrices are contained in PSL2R, but not contained in PSL2Z. And we'll see more in a minute about exactly how they, well, I'll write it down in just a second, exactly how they play out in a particular example. But in general, you're in PSL2R, not in PSL2Z. Okay? So the expense is that you've had to leave integral valued 2 by 2 matrices. They were integral valued 3 by 3 matrices, but when you pass to the symmetric square root, you have to do that kind of extension. Okay, so let's make this totally concrete now in the case of L equal the lattice that we call M sub n. And M sub n is H plus E8 plus E8, that's already rank 18, plus minus 2n. Okay? Now, that minus 2n can and should remind you of this 2n. Okay, and there's good reason for it, because when we start talking about mirror symmetry, these are the basic families of polarized K3s, and L-polarized, MN-polarized K3s are their mirror families. Okay. All right. So in this case, as we said before, the rank is 19, so we have a one-dimensional moduli space. In fact, the moduli space of MN-polarized K3s is nothing but the almost modular curve called x naught of n plus. Okay, I say almost modular because it's not a classical modular curve. So this is upper half plane quotiented by gamma naught of n plus. And I want to compactify the thing. Okay, so what is gamma naught of n plus? So gamma naught of n plus is gamma naught of n union with respect to tau sub n, another copy of gamma naught of n, where tau sub n is the Fricka involution, minus 1 over square root n, 0. Okay, so this is the Fricka involution. Okay, so you see how that's going to take you outside of the integers because of that square root of n. Now, the second feature, one of the key features, I guess, but the second one we want to emphasize for elliptic curves, the first was the realization of the J-line as a modular curve, but the second is the realization of all elliptic curves with a normal form. So in this case, we have the Weierstrass normal form for cubics. So question, so what about normal forms for L-polarized K3 surfaces? Okay, it's a perfectly reasonable question. We have such a thing for elliptic curves. We should want it for L-polarized K3s, and especially for MN-polarized K3s, since they're so close to being the elliptic case. Now, this is as written in the case where L equal Mn, a collection of countably many questions, right? For each Mn, you can ask this question, okay? And you can reasonably expect that you might have to check it for each Mn. You might have to find one for each Mn. Okay, well, certainly the answer you get by finding a normal form for each Mn will be tailored to that specific Mn lattice polarization. But the notion of lattice polarization suggests an alternative answer, which would be a single question, okay? And that single question is, ask the question for the lattice M, which is H plus E8 plus E8, because this is a sublattice of Mn for all n. Now, if you think about this quotienting procedure, you see that lattice inclusion leads to a reverse inclusion of moduli spaces. So if we have a normal form, so we'll say this, we'll say all Mn polarized K3s are M polarized. Okay. It's not obvious that it's unique up to automorphisms of the lattice, but it is. Okay. So all Mn polarized K3s are M polarized. So instead, find a normal form for M polarized K3 surfaces. All right, so let's do that. Well, okay, so before I erase any more on this last board, tell me, so M has what rank? Read it off there. And those E8s are negative definite, of course. What's the rank of M? This is the interactive portion of the course. Okay, so that's 8 plus 8 plus 2. So it's rank 18, okay? Which means the dimension of the moduli space associated to M polarized K3s is 20 minus 18, or 2, okay? So what we're actually looking for is constructing a normal form for M polarized K3s such that we have a two-complex structure deformation, or two-complex structure dimensional moduli space, okay? And then the MNs will sit in there as special curves, okay, on this modular surface. So here's a theorem I proved a number of years ago with Adrian Klinger. So every M polarized K3 surface is isomorphic to a K3 surface from the family of resolved cortex. Okay, so this is canonically ADE resolved, so there's no choices involved here. Okay, and here's the singular cortex family. X, A, B, D. All right. Now, what I'm about to write down, I want you to think of as being analogous to the Weierstrass normal form for elliptic curves, because it is in every respect. So, y squared ZW minus 4x cubed Z plus 3a. I'm putting a little underline there so you recognize it as a parameter. X Z W squared minus 1/2 D Z squared W squared plus W to the 4th plus B Z W cubed equals 0. And that's A, B, and D, complex numbers, and D unequal to 0. Okay, so what is D? Well, okay, you can ask, why is it A, B, and D? Okay, so the easy answer for why it's A, B, and D is that D is the discriminant. D equals 0 is the discriminant. Okay? The much cuter answer is that there's an extension of this family involving A, B, C, and D, and that extended family will capture abelian surface moduli, but that's neither here nor there at the moment. The next feature of this is that A prime, B prime, D prime is equal to lambda squared A, lambda cubed B, lambda to the 6D. So we're actually having a parameter space realized as weighted projective 2, 3, 6. Okay. So think of this as the analog of the J-line, in the sense that what is the J-line but weighted projective 2, 3? That's exactly it. It's 2, 3. Okay. Okay. And then, of course, you want some real teeth here. So, and conversely. All such X, A, B, D admit, in a natural way, polarization by M. Okay. Moreover, we get a modular parametrization. Okay. So what does that mean? Well, it means that the parameters A, B, and D have a natural interpretation in terms of the quotient procedure, okay, this arithmetic quotient procedure. So what I mean by that here is that so the parameters A, B, and D can be expressed in terms of modular functions on the quasi-projective variety. Okay, so now I want to present pre-compactification, the quotient of the type 4 symmetric domain, two-dimensional in this case, by the corresponding arithmetic group. So to keep my consistency with sides of writing things, so there's an exceptional isomorphism between a type 4 symmetric domain of dimension 2 and the product of upper half plane cross itself. Okay? And the quotient is by, okay, well, PSL 2Z cross PSL 2Z, okay, semi-direct product Z mod 2Z. Okay, so what is all this? So the factor here acts as PSL 2Z on this factor. The factor here acts as PSL 2Z on this factor in the usual fashion. And the Z mod 2Z does the only thing it can, which is switch the two factors. Okay? So if you want to, you can think of this as a really, really silly version of a Hilbert modular group. But I mean, it's not literally a Hilbert modular group. It's even sillier than that. Okay? So what are the natural modular parameters here? Well, if it were just PSL2Z cross PSL2Z as a quotient of H cross H, it would be two copies of the J line. Call it J1 and J2. Okay? So if I let J sub I be J of tau sub I, okay, for I equal 1 and 2, where you think of tau 1 as the parameter here, and tau 2 is the parameter there, well, then those would be fundamental modular parameters. But we have the additional semi-direct product by the Z mod 2Z, so it's elementary symmetric polynomials in J1 and J2, and we'll give those names. We'll call them pi, which is J1 times J2, and sigma, which is J1 plus J2. Okay, so the claim here is we get a modular parameter. The parameters A, B, and D can be expressed in terms of modular functions on the quasi-projective variety. Well, here are the modular functions, sigma and pi. So I can write A, B, and D as functions of sigma and pi, or I can write sigma and pi as functions of A, B, and D. So let's do that. So that equals A cubed over D, and this one equals A cubed minus B squared plus D over D. Done. Okay? So this is the complete analog of the expressions for the invariant J in terms of G2 and G3. Okay? Because just as we had G2 and G3 as redundant parameters corresponding to wave projective 2, 3, right? They were giving you two parameters. We have a one-dimensional moduli space giving you weighted projective 2, 3. Now we have A, B, and D as redundant parameters giving you 2, 3, and 6. They work exactly the same way. And now, just as before, we had the single invariant J in terms of G2 cubed over delta, which was G2 cubed minus 27 G3 squared, the analog of D. Now we have sigma and pi, the fundamental modular invariants, reciprocals involving polynomials in A, B, and D with the denominator D in each case. So it's beautiful. It's a complete analog. Okay? Now, you might say this is too good to be true, or rather too good not to be true for a better reason. Okay? So there is a geometrical reason behind this. There are Hodge theoretic reasons, a geometrical reason. So the geometrical reason is that X, which is this minimal resolution that you get resolving the ADE singularities, is actually what is known as the Chiota-Innes surface associated to E1 cross E2, where E1 and E2 are a pair of elliptic curves. So if the j function j1 matches e1 and the j function j2 matches e2, then this Shiota indice k3 is the answer. Now, I could stop here and just say this is the k3 surface that is Hodge isometric to e1 cross e2. Or I could be a little more specific about geometry and say that this is actually built from the Kummer of e1 cross e2. So this would be take e1 cross e2, right, and quotient by plus or minus the identity, and you get those 16 fixed points we talked about before. You could realize this is a singular quartic if you wanted, but you don't have to, with 16 ordinary double points. And the Kummer is the associated variety that you get by resolving. Okay, that's a well-defined thing, but you quotiented by plus or minus the identity, which means you introduced a level 2 structure. The Hodge structures are not isometric. They're off by a factor of 2. So you fix that either by taking a double cover or by taking a further quotient and resolving. Okay? Either way will work. Usually you think of it this way, though, as quotienting by this thing called an Coulomb involution. And then you want to resolve the whole thing. Okay, so this has 8 fixed points in very specific places. And the resolution there gives you a K3 surface, which is smooth, and that is the Shiota indice K3. Okay. So, so far so good. So this gives us a normal form for M. Now, what happens if you really care about, as we opened with, M sub n? Well, we have to figure out where those M sub n polarized K3 surfaces lie. So if X is a K3 surface polarized by the superlattice Mn, then X, we already said, I'll say it again, can be expressed as the resolution of one of the X, A, B, D. Okay? But that's one. What about the whole family? Okay? I know that there's a modular curve's worth of these things. Where are they? So, in fact, the subvarieties of the A, B, D domain corresponding to Mn polarized K3 surfaces are, this is not obvious, you have to check it, are the Mn. Okay, i.e. the degree of the map from the moduli space of Mn polarized K3s to weighted projective 2, 3, 6 is 1. So in this sense, we've gotten the best possible answer to our question of, oh, is there a normal form? We've gotten a normal form, we've gotten the modular parametrization for that moduli space of M polarized K3s, and we've gotten a unique realization of each Mn as a modular curve on this modular surface. Okay, so it's really the best you could possibly have asked for. So what are these things? Well, these are the classical modular curves of Fricka and Klein. Okay, corresponding to a pair of elliptic curves E1, E2 with a fixed cyclic anisogeny. So in other words, tau 2, if you like, is n times tau 1. Now, this is a nice way to think about them. Okay? I should point out, so note, okay, there exist very, I was going to say the word ugly, let's just say complicated, okay, because beauty is in the eye of the beholder. Very complicated, no one's going to argue with that, equations for the image of Mn for n large. In fact, this complexity was the original motivation for developing the theory of modular forms. So when I say complicated, I mean that the coefficients of these defining equations, which remember, you can think of as sitting in a weighted projective space. So it's a bit like just defining algebraic curves or projective algebraic curves. It's weighted projective algebraic curves. The coefficients are all going to be rational. So that means after scaling, the coefficients are all integers. But these integers grow so rapidly with n that it becomes very difficult to even compute them. Okay? Much less to write them down on a page. All right, so far so good. So what we have now is a dictionary that applies to a class of K3 surfaces that naturally generalizes that of elliptic curves, a dictionary between algebraic data and transcendental data, okay, or at least algebraic data and period data hidden in the sort of Hodge structure that's packaged in the tau 1 and tau 2. Okay, or if you prefer, the J1 and J2. So now the next question becomes, twofold. Well, first of all, is there a way to capture these very complicated equations, okay, really capture them, without actually having to write them down, okay? Also, I would say, is there a way to make that dictionary between algebraic and transcendental structure more manifest? So I'm talking around the words Picard-Fuchs equation here, but since it's in the title of my talk and it's already on the board, let me just say it. Okay, so what we want to do next is to look at Picard-Fuchs equations. Okay, these are differential equations which come from the variation of Hodge structure of these Calabi-Yaus in families, and they annihilate periods of the holomorphic top form over middle dimensional cycles. Okay, so as always, let's start with the elliptic curve case. Okay, so here let's let pi e to b be an elliptic surface. Okay, I'm not going to give the formal definition, but we want only finitely many bad fibers, the usual things you'd expect. The base does not have to be a priori a curve of genus 0, but for our purposes it usually will be. We're going to let sigma in the base be the support of the singular fibers, and I'll let B naught be B minus sigma. Okay. Then we say the functional invariant, this is notation that goes back to Kodaira. The functional invariant, script J, is the rational function on the base B whose value at T and B naught is the J invariant of the fiber E sub T at T. Okay? So you might say, Chuck, we already know a formula for this. You've already given us a formula for this. Okay, because you're jumping ahead and you're saying, yes, we can take our formula for a fiber and based on this definition, extend it over a function field. So here's the answer. So yes, J of T in practical terms is if you have a wire-stress normal form presentation for your elliptic surface, g2 of t cubed over g2 of t cubed minus 27 g3 of t squared. So it's the function field theoretic version, okay, of what we had before. And this is in terms of the wire-stress normal form, which, let me just remind you, is now y squared z equals 4x cubed minus g2 of t x z squared minus g3 of t z cubed. Okay, and that's 3 sub t. Okay, now the functional invariant is only part of what captures the structure of this elliptic surface. The other part is a sheaf known as the homological invariant. So the sheaf, script g, r1 pi lower star z restricted to b naught. So what is that? It's the integral local system whose stalks are given by the first cohomology groups h1 e sub tz. Okay? So this sheaf is called the homological invariant. And we'll do more on this on Thursday. Okay? This is useful to note. It is characterized, this local system is characterized by its monodromy representation. I'm just going to use rho, but I've already used, you can tell the difference between these. I'll call it phi. Phi, pi 1 b naught to SL 2z. So usually you just think of the monodromy representation when you're talking about the homological invariant. Okay? Now, what we want to consider to get our hands on the Picard-Fuchs equation is the weight 1 integral VHS associated to the homological invariant G. Now, I want a polarization, but I get polarization on the Hodge structure on the VHS via cut product. So that part's good. If I pick a dual basis in H upper 1 to the standard alpha beta basis, then the matrix of the polarization is just the 0, 1, minus 1, 0 matrix. The Hodge filtration is just determined by a non-zero class in H upper 1 ETC, and that'll span F1 for our Hodge structure. And then if I write explicitly a period as Z1 alpha star plus Z2 beta star, where again alpha star, beta star, dual basis to alpha beta in H1 ETC. Okay, then the Hodge-Riemann bilinear relations tell us, it goes both ways. Tell us that this is equivalent to, well, let's just say the Hodge-Riemann bilinear relations are themselves equivalent to the statement that Z2 over Z1 lies in the upper half plane. Okay, so that's clean. So now that we have this variation of Hodge structure, what are we going to do with it? Well, we're going to use the VHS to produce an ODE. And this ODE is going to live over the same base as the family of elliptic curves. We have this beautiful local system, so we have the Gauss-Minian connection, and we're going to just apply it. Okay, so the VHS is going to give us a Fuchsian, okay, i.e. regular singular differential equation known as the Picard-Fuchs equation. Okay, and just to be absolutely clear on what we're doing, if we let omega be dx over y, using our notation for the wire-stress normal form, that's our standard holomorphic 1 form, and nabla the Gauss-Manin connection on G tensor C. Well, because the rank of GC is 2, there exists a linear relation between two things, among, okay? Among omega nabla ddt, omega, and nabla ddt squared, omega. Okay, so that gives us A of t nabla squared dt omega plus B of t nabla dt omega plus C of t omega equals 0 for rational functions A, B, and C. No relation to the ABs or whatever I talked about before. All right. And of course, if you have a cycle in H1, say gamma in H1, you can make this concrete and actually determine functions which are the associated periods of the holomorphic form, dx over y, over that cycle. And then you derive the differential equation, which is known as the Picard-Fuchs differential equation. So I'll just say fix gamma in H1 ETZ and f sub gamma of t defined to be the integral over gamma of omega. Okay, and then you get A of t d squared f dt squared plus B of t df dt plus C of t f of t equals 0, and this is what's typically called the Picard-Fuchs differential equation associated to the family of elliptic curves E over B. Okay. Now, that's fine and good, but practically speaking, it doesn't tell you one whit how to compute it. Okay? It gives you hints maybe, but it really doesn't tell you a procedure. So how to compute the Picard-Fuchs differential equation. All right. So the strongest hint is this notion that there is going to be a linear relation among these. It's a defining condition in some sense. Okay? So if you can produce, perhaps redundantly, a collection of quantities that live in the same space and are overdetermined, and if you can argue that a relation must exist based on degree considerations or dimension considerations, then you might be able to cook up an algorithm to do this. Okay, so anyway, this is the hint from all this. And the algorithm, which I won't go into detail about, is often referred to as the Griffiths-Dwork algorithm. Okay? And there's one key idea, well, two key ideas, but the key in some sense, I'll say the key in some sense, is the Poincare residue trick. Okay? I have to pick one key. This will be it. The second trick is reduction of pole order. But the first trick is the Poincare residue trick. And the Poincare residue trick is just the statement that the integral you want on the hypersurface is equivalent to the integral of a meromorphic form on the ambient space with pole along the hypersurface. Okay, in other words, it sounds a lot like residue calculus, which is really what it is. Okay, you're doing a computation on the hypersurface by doing a computation strictly off the hypersurface, but with something that is polar or 1 along the hypersurface. Okay. Now, there are two names attached to this algorithm, Griffiths and Dwork. Dwork famously applied this in the p-adic realm to some very specific and very important pencils of Calabi-Yau manifolds, starting in complex dimension, or starting with elliptic curves and then working his way up with K3s and Calabi-Yaus of all dimensions. Griffiths turned it into an algorithm that works for any family of generically smooth projective hypersurfaces. Okay, so the condition on smooth projective hypersurfaces can be generalized, and has to be for a lot of application. So in a result with Harder, Mobasati, and Witcher, okay, we observed that you can apply it, so we can generalize to generic quasi-smooth hypersurfaces in any weighted projective space. Okay, and we specifically applied it to generic anti-canonical K3 surfaces in Reed's list of 95 weighted projective threefolds. Okay, in his list are weighted projective threefolds with the property that their generic anti-canonical has, in a natural way, lattice polarization of type M that we talked about, and also lattice polarization of a weaker rank 17 lattice polarization, which is the one that corresponds to principally polarized abelian surfaces via the Schrödinger construction. So it's really important to be able to do this in effective terms. Let me just check the timing. So I think there's going to be a little bit of asymmetry in how much time I spend on the first half and the second half. We could take a break now, maybe 5-minute break, and then we'll pick up and I'll finish this and start the next one. Is that okay with everybody? Yeah. Well, I can power through. So 5 minutes? Okay. So we'll start again at 10 past. Do I have to touch anything to make it?
So yeah, continue.
Okay. How do you do that? It says status recording. Good? Okay. Okay, great. So so this is not technically part 2 yet, but let's finish part 1. Now that we've had our break. So let's look again at the elliptic curve case. Okay? And I want to take what is sort of a moduli theoretic approach to computing Picard-Fuchs. Okay? So we know we can do it, right? I mean, the Weierstrass normal form is going to satisfy Griffiths' theorem, right? Fine, we can do it, okay? The exercise, it's fun to do. But instead, why don't we take a moduli theoretic point of view and say, well, wait a minute, the J-line is somehow the fundamental moduli space for complex structure for elliptic curves. Can we take a local system on the J-line and use the functional invariant that maps to the J-line to deduce the structure of the Picard-Fuchs differential equation from that? Seems not entirely unreasonable. The only quibble you might have is that J does not does not capture fully G2 and G3. Okay? J captures G2 cubed over delta, but it doesn't quite capture G2 and G3. And you might need all of G2 and G3 to fix the answer, to make it right. And we're going to see that too. Okay? So I'm going to give you a non-standard but edifying description of how to get Picard-Fuchs for elliptic curves. So consider the special family. sort of over the J line. I'll call it E mod over T1, okay? And I'm going to get into trouble with my index, my running variable name, okay, on the target, but I'm going to call it T for now, and then rapidly I'll change it to J. So consider this family, y squared z equals 4x cubed minus 27t over t minus 1 x z squared minus 27t over t minus 1 z cubed. And you may have seen this in literature before, okay? This special family has the marvelous property that when you compute j of t, okay, for E mod, you find that j of t is exactly t. Okay. So for this reason, we call t here j. Okay, what is the j line variable? Okay, great. Now, for any elliptic surface E over B, we know we have this functional invariant map script j, okay? And it really is mapping to the j line, if you think about how it was defined. So for any pi e to b, we have a nice picture like this. So there's our E over B, okay? Here is our multi-valued morphism to the upper half plane, coming from taking tau 1 and tau 2, or the ratio tau 2 over tau 1, whatever you want to say. Mapping this down then to P1j, the j line. The composition of these two is a rational function j of t. And over here, I just built E mod. Okay. So what could be more natural than to compute a differential equation here, pull it back to here via this j of t function, and then somehow correct it? Because you can't expect to be lucky enough that the pullback is going to spot on give you Picard-Fuchs. Okay? In particular, we know j only sees g2 cubed over delta. It doesn't see g2 and g3. Okay, so theorem. I'm not going to call it a theorem. I don't even call it a proposition, but it's something that I made sure appeared in the thesis, which has been turned in by my current PhD student, who's going to be a postdoc at Brown in the fall. So this is an easy result, not a hard result, but you won't find it quite stated like this in the literature. I don't know if this goes back to Peter Stiller or goes back to the ancients, but I would probably reference Peter for this. The pullback of the Picard-Fuchs differential equation, E mod over P1j, okay, dot, and this dot means scale solutions by the square root of g2 of t over g3 of t. Okay, so what does this mean? Well, first of all, this bit, Picard-Fuchs differential equation, E mod over P1j, this is nothing but a particular 2F1 ODE, Gauss hypergeometric ODE. I won't tell you which one, that's an exercise. Okay? But you can find that in literature too. So 2F1, this is a 2F1 equation. So what's easier than that? You have a 2F1 equation on P1 with three punctures. You pull it back by this rational function, and then you say, oh no, I'm not quite right. Well, all you have to do is multiply the solutions, scale the solutions by the square root of g2 over g3, and you're done. Okay? And you can understand what's happening if you study the Wronskian. Okay? If you look at the Wronskian differential equation associated to the Picard-Fuchs equation. But this is the gist of it. Okay? Now, why did I put that up there? I put that up there because almost exactly the same thing is true for MN polarized K3s. So generalization to MN polarized K3 surface families. Okay? Again, you have a uniformizing differential equation in the sense of Poincare, a UDE, for the moduli space of MN polarized K3s. okay, of rank 2. So remember, the symmetric square root of the monodromy for the Mn polarized family of K3s, right, is 2 by 2 matrices. And that's what we're talking about here, okay? And you get a uniformizing differential equation that's the analog of this equation here. You get that the sim squared, and this is natural from what I said earlier, of the uniformizing differential equation UDEN has rank 3, of course. And the statement now becomes that the Picard-Fuchs differential equation of a family of K3s of Mn polarized over B is going to be some generalization of the functional invariant pullback sim squared UDE sub n, okay, and then we're going to twist it by now a cube root of some function g of t. This is scale solutions by, okay, and this g of t is in rational functions on B naught. Okay. And the g of t is known in terms of the normal form and dot, 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 dot. Everything else is exactly the same. So the story of uniformization via Picard-Fuchs differential equations can be run both ways. You can either take a family of varieties whose period map is surjective that covers the entire moduli space, compute the Picard-Fuchs differential equation, and then deduce a uniformizing differential equation or uniformizing differential system for the base variety, okay, which is the moduli space. Or, if you know what you're doing, you can actually run it the other way. You can figure out what information you need beyond this generalized functional invariant and this special local system on the moduli space to deduce the actual structure of the Picard-Fuchs differential equation for your family of varieties. Okay, so that's kind of an important step there. Now, this is fine if we had a model that we were working in for Mn polarized K3s, one curve at a time. But that's not the normal form we were talking about. Remember, we were talking about working with the two-dimensional moduli space of M polarized K3s, and then concluding properties of the Mn polarized K3s curve by curve by curve by curve. We get all of them, but it's curve by curve by curve by curve. So, what about these moduli space of Mn polarized K3s sitting in moduli space of M polarized K3s? Okay. What's the relationship between the uniformizing differential equation for this modular surface, which is the similar information to the Picard-Fuchs equation for the two-parameter family of K3s, and the characterization of the jump loci, these modular curves sitting inside it? Okay. So what we'll do is we will apply the Griffiths-Dwork algorithm to what I'll call probes into moduli space of M polarized K3s to detect special subloci in moduli. Okay, so specifically, here's the strategy. We construct, so the steps. So construct a moduli space of L polarized K3 surfaces. Okay. We can safely assume for simple examples that it's globally rationally parameterized, that it's actually a rational variety. That will fail eventually if you get to more and more complicated examples, but for the simple examples we'll be working with, it's true globally. In fact, we can do one for which a weighted projective anti-canonical normal form exists. Okay? Okay, next step is consider a mapping of the t-disk into the moduli space. Okay. And I literally mean a disk. It doesn't have to be global. Okay? I just mean you have a little t parameter on a complex disk, and I'm mapping it in. Okay? It's going to still work. And then we apply Griffith's work in its of t form, if you like, sort of the function field form. So what will happen is you'll get an ODE. That ODE will generically have rank equal to 22 minus the rank of the Doran-Severi for L, so the rank of L. So 22 minus rho. And the loci where your disk is going to hit a special subvariety, that rank will drop. But since this is completely explicit, you'll be able to read off the coefficient of your ODE that needs to vanish for your rank to drop. And that'll be your universal condition for the rank dropping. Okay? So let's do it by example with M-polarized K3 surfaces. Okay? So if you take a chart with A unequal to 0, then you can actually write out d squared db squared omega minus 4d d squared dd squared omega minus 4 d equals 0. And then this is the full Picard-Fuchs differential equation. 1 minus b squared plus d squared db squared omega plus 2b db omega plus 4bd omega plus 2d. I don't need to write this out, but I just want you to see how explicit it is. Plus 5 over 36 omega equals 0. Okay? This is the Picard-Fuchs system, right? For this family of, this two-parameter family of M-polarized K3s. But we also know that there's a dictionary between the ABD parameters and J1 and J2. So if you plug in b squared equals J1 minus 1, J2 minus 1 over J1, J2, and d is equal to 1 over J1, J2, and now do Griffith's work in its of t formulation, okay, you find that the coefficient of the top derivative term, so of the fourth derivative term, is this thing, 144 J1 of t minus 1, J2 of t minus 1 cubed, J1 of t, J2 of t, to the fourth, J1 of t minus J2 of t, to the seventh, J1 prime of t, J2 prime of t, squared, and then finally times, I can do it here, times what I call box J1 of t minus box J2 of t. Okay, so that's a constant. This is going to be 0 when either one of them is equal to 1. This is 0 when either one of them equals 0. This is 0 when they're equal, because diagonal, right? This is 0 when either one of them is constant. So basically, you can ignore all of this. And what really matters is whatever the heck this is. So what is box? So where box j of t is equal to j prime of t squared times 36 j of t squared minus 41 j of t plus 32 over 144 j of t minus 1 squared j of t squared plus 1/2 the Schwarzian derivative j of t t. I won't write out the Schwarzian derivative. Okay. So the condition now for rank jumps in the n-polarized family becomes exactly the condition that box J1 equals box J2. Okay? And proposition, okay, J1 of t, J2 of t is a local holomorphic parametrization of an algebraic curve satisfying box J1 of t equals box J2 of t if and only if the curve is a modular curve M and N for some n. So what we see here is the first example of a universal differential algebraic criterion for rank jumps. Okay? This condition, box J1 equals box J2, box J1 of t equals box J2 of t, is, of course, nonlinear. But its algebraic solutions are precisely the modular curves. Okay? So it's a nonlinear differential equation whose algebraic content is the classical theory of modular curves. Okay? So obviously, when you see a theorem like this, you have to try to generalize it. And so we proved it, and the question was how to generalize it. And the approach we took was to first of all generalize this step, right, of figuring out the Picard-Fuchs differential equation for L-polarized K3s. And secondly, to sort of understand how to relate that formalism with the natural Hodge theoretic formalism for such rank jumps. Okay? So since I'm going to completely run out of time for the second half of my talk, I'm going to simply state a result here, okay, which is that, okay, so I'm going to simply state the result this way. I'm going to say this generalizes to L-polarized K3 surface moduli. Okay, and the key thing here is that we provide a differential algebraic characterization of totally geodesic subvarieties of the moduli space of L-polarized K3s of two types. Okay, and the types are where it's sort of the linear type and the orthogonal type. So I'll say orthogonal and unitary. So orthogonal type and unitary type. Okay, and the trick here is in the orthogonal type, the totally geodesic subvariety, I'll call that script S, is actually an open piece of a quadric. hypersurface in a linear subspace of the projective period domain. And in the second case, S is an open, or S is equal to an open piece of a linear subspace. Just go like that. Okay? And these are the two types that come out, and you get separate but equally easy differential algebraic criteria for each of these. Okay. So in the half an hour that remains, let me jump to the other part of the talk. So what we've done so far is we've introduced Picard-Fuchs equations for families of Calabi-Yaus. Okay. We've specialized in the case of Picard-Fuchs for L-polarized K3 surfaces. And then we've asked questions about, so we've answered questions about Picard-Fuchs detecting special subloci. Okay. Now I want to ask a new kind of question, which is, what can Picard-Fuchs equations tell us about the geometry, that's Hodge structure, of the total space of the family? So think about it, right? I've got a family of Calabi-Yau varieties. I've got a Picard-Fuchs differential equation. It could be an ODE in a one-dimensional family. We'll assume that for now. Or it could be a complicated PDE system, still Fuchsian. And it's completely natural to think about properties geometrically of the total space of this family. Okay? Is that a rational variety? Is it a Calabi-Yau variety? Is it general type? Who knows? Okay? At the very least, you might expect that the internal variation of Hodge structure for this family of Calabi-Yaus would know enough to tell you this information. So broadly speaking, what we're trying to do is we're saying, look, we're going to pass from differential equations, okay, to Hodge theory. Now, we're not going to reproduce everything, but we'll constrain Hodge theory. And then we'll use the Hodge theory to further constrain geometry. Okay? So as a geometer, it's reasonable for me to say that geometry knows more. Okay? So passing from geometry to an underlying Hodge structure is losing information. And from the underlying variation of Hodge structure, say, to differential equation is losing information. And we want to understand to what extent we can go back. Okay? If only to constrain the possibilities. Okay. This is particularly important if the geometry you're after happens to be Calabi-Yau threefolds. Because as we said, we know very little about the geometry and topology of Calabi-Yau threefolds. We don't even have a bound on the Hodge numbers. Well, that's how clueless we are. All right. So what I want to do now is this. Let's let X be a variety with a projective morphism I. X, I called it B before, but now I really want it to be a curve, so I'll call it C, whose fibers are generically Calabi-Yau of dimension of X minus 1. Okay? And I want to ask the question, when is X Calabi-Yau? Okay? So if I specialize this to the case of families of elliptic curves we were talking about earlier, so that would be, so dimension x equal 2, this is asking when is an elliptic surface K3? That's the analogous question. Okay? So if I have the analogous question with the answer there is that C has to be CP1, right? You could just say, I'll just say Euler characteristic equal 24. Okay? Or if you want to do that in a more algebraic way, you say that there exists, so i.e. there exists a line bundle L over C such that X is actually a hypersurface in P OX plus L squared plus L cubed and omega X. Is the I'm switching notation to omega for the canonical bundle, just so you know, is pi upper star omega C tensor L. Okay, with L equal omega minus 1 B1. Also names of 2. Okay, so that's the answer in the case of K3. It's telling you exactly when a Weierstrass elliptic elliptic surface will be a K3 surface. Okay, so this is the answer. Okay, but as you might expect, it's going to be a lot more complicated if you're talking about threefolds. Okay, so I want to consider. So I want to consider now rank 19 polarized K3 fibrations. Okay, the most important rank 19 lattice for me will be Mn. Okay, but it doesn't have to be Mn. I could pick one of the ones whose modular curve is a Shimura curve. It would still work. What I mean by this is that the image of H2X, X is now the threefold, to H2F is rank 19 for a smooth fiber F of pi. Okay, so I want to consider those. And a motivating example, well, if the most famous Calabi-Yau threefold is the quintic threefold, quintic hypersurface in CP4, the next most famous Calabi-Yau threefold is the quintic mirror. So mirror quintic Calabi-Yau threefolds. Okay, I'll use this sort of slightly modern Linda Ginsburg-ish approach to writing it down instead of Green and Plesser. X plus y plus z plus w plus u to the fifth minus t x, y, z, w, u equals 0, okay, in P4. So this is a pencil, all of whose members are singular, okay? And so, of course, I have to resolve the singularities to get something smooth, but once I've done that, generically, I'll get something smooth, which will be the so-called mirror quintic family, and there will be some bad fibers in there as well, okay? Now, why am I writing down this? I'm writing down this to be the x. Okay, so this is going to be our x. And my claim is that x, okay, so every x in this family, by which I mean the resolved ones, admits at least 2 distinct rank 19 lattice-polarized fibrations. Okay? So M2 and M3, for example, show up in this case for the individual Calabi-Yaus. So let's give ourselves some notation for what follows. So notation, oh, that's bad. Notation. So I'm going to let X be fibered over P1. X is our Calabi-Yau threefold, putative Calabi-Yau threefold. It's a threefold in any case. Mapping down by pi to P1. P1 is there because if it were not there, there'd be no chance of the fibers, by K3 fibers producing a Calabi-Yau threefold total space. Let's let U in J be the complement of the critical locus for pi. We'll let this be pi upper naught, which is just the restriction. Pi restricted to x naught. X naught is then the full inverse image of U. Okay, did I get that? Yeah, got that. And this goes in here. Okay, good. And the condition of rank 19 polarization implies that R2 pi naught lower star Q splits as a copy of what is morally the transcendental lattice and QU19, okay, with the rank of T equal to 3. So that's 22 minus 19. Okay. This splitting goes hand in hand with this notion that the family should have trivial monodromy and algebraic cycles. Then there is a VHS on U of weight 2. Okay, underlying this. And the theorem by Zucker is that if V is a VHS on a smooth quasi-projective curve U, J U into U bar, it's smooth compactification. Then HI J lower star V admits a canonical pure Hodge structure. Okay, so let's just think about what this gives us. This is telling us that we can start from, well, I'll do it in our case. We can start from our T, right? And we can consider H1 J lower star T, for example. This is what's known as the parabolic cohomology. Okay? And what Zucker is telling us is that the parabolic cohomology admits a pure Hodge structure. Okay? And the weight of that pure Hodge structure is 1 higher than the weight that we started with. So it allows us to ratchet up from weight 2 to weight 3. So furthermore, H3XQ, whatever X is isomorphic as Hodge structures to H1 J lower star T, direct sum some little piece H. This guy is a weight 3 Hodge structure with H30 equal H03 equals 0. Okay? But what that means is that H03 of X is equal to H03 of the parabolic cohomology of T. So this is great news, okay? Because what this tells us is that if you're trying to show that H03 of X is compatible with it being Calabi-Yau, i.e. is equal to 1, it's sufficient to check H03 of the parabolic cohomology of the internal vibration, the internal variation by K3s. Okay? So this is amazingly useful, okay, as a constraint on the geometry of threefolds. Right, so the goal then is to compute H03, H1, J lower star T using Picard-Fuchs equations. Okay. Now, just a quick reminder, that T we're talking about is literally one of those order 3 Picard-Fuchs equations we were getting from a family of rank 19 K3s. It's exactly what we were getting. Okay? So we have a great deal of control over that, and that's what we're going to be making use of now. Okay. So, right. Now, I have used the word Fuchsian to refer to these differential equations, and I've said the words regular singular, but let me just indicate a structural consequence of the regularity of the singularities of the Picard-Fuchs differential equation. And that structural consequence is that, so remark, because of regularity, we can write the Picard-Fuchs differential equation for a family of varieties, in this case for our rank 19 K3s, as delta cubed plus g2 of x delta squared plus g1 of x delta plus g0 of x, where delta is x ddx, and the GI have no poles at x equals 0. Okay? So, by definition, we say that the local exponents of the Picard-Fuchs differential equation attached to x relative to some form, a 3-0 form in this case, or I guess this is a 2-0 form of the fibers. At x equals 0 are the roots of this indicial polynomial. So roots of the polynomial t cubed plus g2 of 0 t squared plus g1 of 0 t plus g0 of 0, denoted mu I naught. Okay? Now, this is kind of important, and I have to say I didn't fully appreciate it until this project, but you have to order them in non-decreasing fashion. Okay? You don't think it's important, this indexing, but it turns out to be critical. So you then define the Riemann scheme of the Picard-Fuchs differential equation to be, well, a list of the regular singular points, P1 through Pn at the top, and then in the columns, these mu's, mu1, P1, mu2, P1, down to mu, let's say there's m of them, let's say it's rank m. So for us, m equals 3 for us. Okay, so mu m P1 all the way up to mu1 Pn, mu2 Pn, down to mu m Pn. Okay, so just as an example, to make sure that we're all kind of on the same page, we say if X is a quartic mirror, the quartic mirror K3 family, given by, okay, it's a pencil, so it's S, and it's done exactly the same way as the quintic was we did before. So it's S times X plus Y plus Z plus W to the fourth minus T XY ZW equals 0 in P1 cross P3. P1 has the ST coordinates and P3 has the XYZW coordinates. then the Picard-Fuchs differential equation is delta squared plus t, delta plus a quarter, delta plus a half, delta plus 3/4. And the Riemann scheme, well, the regular singularities are at 0, 1, and infinity. And you get 0, 0, 0 at 0, 0, 1/2, 1 at 1, and 1/4, 1/2, 3/4, and infinity. Okay. So a result of mine with Harder and Thompson now addresses this question of these sort of structural implications of the Picard-Fuchs differential equations on what amounts to the parabolic cohomology of the total space, or the parabolic cohomology attached to the family. So here we go. So theorem. Okay, let's let delta be the singular points of the Picard-Fuchs differential equation. Let's let a sub f, no, okay, I'm not going to define these, but anyway, a sub 1/2 be the counts of singular points with local monodromy matrices of specified types. Okay, so here I'm cheating, right? I'm not telling you how I'm clumping the monodromy descriptions for these, but they're counts. So once you've listed all the types in sort of Jordan normal form for your monodromies, you can put them into bins, and that's going to give you two numbers. Okay. Then H30 of x is equal to H0 O P1 AF minus 4 minus A 1/2 over 2 minus the sum P in delta, the floor function mu2 P minus the floor function mu1 P minus 1, close parenthesis, close parenthesis, close parenthesis. Okay. So here we're using several things. So first of all, notice I warned you that order mattered in listing, building your Riemann scheme, because we're only using mu1 and mu2, not also mu3. Right? Okay? So for us, m is 3, right? So you have mu1, mu2, and mu3. And the ordering depended upon this non-decreasing condition. So this is important. Don't reorder willy-nilly. Okay. Secondly, what this uses here, so proof uses a result of Eskin, recent result, Eskin, Kontsevich, Moeller, and Zorich. And strongly depends on the way we've constructed it on the rank 19 condition. Not on the MN condition, but yes on the rank 19 condition. And as a corollary, you get, if X is Calabi-Yau, then this count AF has to be 4 plus 1/2 A 1/2 plus the sum P in delta. Floor function mu2p minus floor function mu1p minus 1. Okay? So this places a strong constraint on the geometry of the total space. All right. So we'll have more on this in my second half, part 2 of Thursday's talk. But let me just give a little teaser for that right now. So question, if Z is a K3 surface fibered threefold obtained by base change from, and this is base change up to resolution of singularities, of course, up to resolution of singularities from so there's Z, there's X is on P1, coordinates S and T, this is P1, this will be G. So base change from the rational threefold X that I actually erased somewhere over here, but I'll write it again. S times X plus Y plus Z plus W to the fourth plus T X, Y, Z, W equals 0. Then when is Z a Calabi-Yau threefold? Okay. So now we're specializing to, by complete analogy with the Weierstrass fibration for elliptic curves, where we were sort of taking a modular family on the J line and pulling it back and then asking about properties of the total space. When is it K3, for example? We're doing the same thing here. We're taking this, which is effectively a modular family. This is that quartic mirror family we were talking about earlier, pulling back the quartic mirror family and asking when can the quartic mirror family complete in its total space to give you a Calabi-Yau. And in particular, that's going to subsume the quintic mirror because, as we mentioned, it's of this type. So again, this is mostly a teaser to stick around to the end next time. Theorem with Harder and Thompson. Let's let G from P1 to P1 be a rational map. Y1 through Yn be ramification orders of points over T equals 0. If G upper star X has a Calabi-Yau resolution, then either, one of two possibilities, first case, n equal 1 and y1 is between 5 and 8, or case 2, n equal 2 and y1 and y2 are between 1 and 4. Okay? And furthermore, and I don't have room to write it, so I won't bother since I have no time left, for any G satisfying these properties, G upper star X has a Calabi-Yau resolution with possible isolated terminal singularities. And if, moreover, if the map does not ramify over T equal 1, then it's guaranteed to be smooth. Okay? So, as we'll see, especially in the second half of Thursday, there's an effective method for constructing Calabi-Yau threefolds that are fibered by K3s of high Picard rank, and you achieve this largely by constraining possible geometries through constraining possible Hodge structures, and that came from properties of the Picard-Fuchs equation. So, thank you.
Any questions? No, it's fine to speak, yeah.
Off? I mean, the square?